sort of talking, and maybe we wait for a couple of minutes. Yeah. Zoom section of theme 4, Smart Health. We have 4 lightning talks. The first one will be given by Dr. Haodao Hu from Eli Lilly. And Eli Lilly has been very successful recently because of this new weight loss drug, Zipperbump, right? So becomes the richest company, pharmaceutical company in the United States. And talking about driver's seat, how that is in charge of the AI of this company, and has a lot of vision and perspective from pharma industry to see how this AI can help to develop drugs and how to, innovate this pharmaceutical industries. Then, so how that?
Do I need to wire up or just use this? Okay, good. Okay. Okay. Okay, up and down. Okay. Yeah. So I'm just let me just see. Okay. Okay. So the kind of first questions I've got received is kind of what's the most important thing for the next 5 to 10 years. So I would think kind of when I'm from pharmaceutical companies, the first thing is when the people take the drug. So when people take the drug, when the people get some disease, we take the drug. So this was the current status. But what we truly believe down the road for the futures, we can predict when the patient get the drug. We can predict when the patient get a disease, so we can have the intervention much early on. So if that is true, actually in many of them, this is already happening in many of the kind of maintenance. The maintenance doing the so-called predictive maintenance, and so we can predict when we really need to change the engine oils and change the kind of replace part of this kind of the parts to improve the performance. So this is one of the problems that we truly believe that will be happening in the futures. But to talk about this is kind of the next question is what's the important problems and what's the future. I'm just going to talk about the big problems, what I truly believe in the 5 areas. So these 5 problems, I'm going to talk about high-dimensional data distributions and how can we estimate this, because this is really truly the fundamental of many of the research problems. And later on, I will describe some of these potential open problems that we are looking for some of the collaborations. So we know for the generative AIs, and people can put the prompt and generate the pictures. But actually, generate the picture is the fundamental to generate the picture is to estimate underlying the densities of the data. So we already have many of the publications. They already have many of the publications. I'm not going to review this, but in high levels, these are key things we can view at the generative AI to understand the underlying the density. This is kind of the very challenging problem for statistics. And kind of during the past 2 days, during the past yesterday and today, many of the talks are related to this one. For example, and in Annie's talk talking about the differential privacies, and in the kind of how can we get high-dimensional correlated data estimation? That's a very challenging problems. And Susan just talking about the digital health. If we do the offline reinforcement learnings, there's many of the missing data problems, and some of the patients even partially observed. How can we do the data imputation and correlated data imputation? That's another challenge. So think about this image generations is a part of this generated high-dimensional correlated data. During the past, statistics is very difficult to handle these problems. Right now, because the generative AI, they already have some good framework, some problem. I'm going to quickly review this and also talk about what's the implication in the statistics. So here is one of the approaches to doing this called a diffusion-based solution. The general idea is to map the pictures to some completed noise. And so to doing this is they go to one step after another, have the original picture and continue to add the noise. And then we can use a neural network to learn the backwards. So this approach put in the formulas is in the very simple formula like this one, and people probably familiar with this and have the kind of training step, and also kind of reverse learning the noise. That's another approach, kind of equivalently another approach called score-based solutions. And so because if we learn the high-dimensional densities, one of the challenge of learn the high-dimensional density without loss of generality, we can write in the top. But the problem is handle the denominators, kind of is normalizing constant is a challenge. But on the other side, they take the derivative of the log PDF, we can get the so-called score functions, and the score function is take the derivative with respect to x instead of with respect to the parameters. By doing this, and once we have this derivative, the score functions, we can recover through the Lagrange dynamic. We can recover the whole high-dimensional densities. By doing this approach, have been achieved a lot of good success. I'm not going to through the details, but in general, kind of the training the problems in the high-dimensional is a challenge, and the people, because they are so sparse, suffer from the curse of dimensionalities. And so the people do a little bit of diffusion process, and after this diffusion, and we can learn the density relatively more accurate. But the problem the point for here is right now we have like a kind of the good framework, put both of these approach under the same framework under the stochastic differential equations. So what we talk about for here is the general form of the stochastic differential equation. And through the approach, and we can form the DDPM, the diffusion-based solution, in one of the special case as the one of the special case of the stochastic differential equation. Another approach, similarly with the score-based solution, is another special case of the stochastic differential equations. By doing that, there's a lot of good implications for statistics to learn the high-dimensional distribution. The one thing is we know that if the forward process is a diffusion process, the backward is another diffusion process. So this is one of the implications. The second implication of talking about for here is the ordinary stochastic differential equation. They can also equivalent to the ordinary differential equations, and by doing this, they can make the trainings much more efficient. So, and by doing this, I'm thinking one of the implications for the statistics, we can better understand these kind of generative AI properties and what they put in the stochastic differential equation framework. I think this area is kind of widely open areas that not many of the statisticians have been doing this kind of the statistical properties. Another kind of thing is also very important for us is kind of this conditional generation. This provide additional framework for the foundation models. And I know this morning people talking about the foundation model. During the past, people talking about the foundation model is primarily through the transfer learnings. But for here, this kind of the bottom equations and it kind of made us very exciting, and they provide an alternative framework. Think about the case is we are interested to talking about this kind of the X key condition on the Y. The Y can be considered about like the prompt, and I write down a bunch of the kind of one of the sentence to generate the astronaut and write the horse, and I want to generate the dog with sunglasses. All this information can be considered as a conditional information. In the field of the digital health, sometimes we measure the partially observed observations for the offline learnings. How can we conditional this information to generate the whole profiles? All of these things can be considered as a conditional generation. But the cool thing for here is the bottom of the equations. If you look at the bottom equation to generate the image, generate the pictures, or generate the high-dimensional correlated data, in the bottom equation, that only one part kind of contains the Y information, all the others that without any of the Y information. So which means we can train one of the foundation models to learn the score functions of log pxt by using a lot of data to learn this. Later on, we can add this conditional information, the Y conditional X. And also, the most importantly, kind of the Y conditional xt, the Y is in the lower dimensions. Either classifier, either kind of can be binary doing the classifications. We can use a much smaller data set to train these classifications at the bottom. So in that case, kind of this provide a good framework as a foundation model to alternative framework to the foundation models that we are kind of using this for many of the areas. So by doing this, kind of they're talking about a few important implications, and we can leverage, put in the generative AI and the framework for the stochastic differential equations, where the tools can handle the high-dimensional PDF and solve kind of either can provide profound indications of many of the statistical problems. And also importantly, they can kind of estimate in the high-dimensional density. They can estimate the precise kind of the data densities for this, and currently we are using this for the outlier detections, the image detection, and also for some of the kind of data imputations. So another approach is how can we continue to expand this? How can we continue to expand this work? So one thing to expand this work is traditionally doing the machine learnings and doing the data. People are doing the data augmentation in the AIs, and if we talk about one method can help to significantly improve the accuracy. People talk about data augmentation in the image. I can rotate this, but many of the data is not in the not in the image, just doing the rotations. For example, in the molecule structures, where in the 3D, we need to consider about the rotation and the translations. So with doing the traditional way, doing the brute force data augmentation is very challenging. But how can we build in this kind of symmetrical information into the machine learning framework that can provide a much more elegant framework? So in that case, that is the framework of extend this to the lead group, to the using the mathematical using the group theory to doing this in the lead group. And so the challenge for here is how can we leverage the group theory to doing this, and how can I still use the generative AI framework? So one part is we know the translation and the rotations, many of the problem belongs to this SE3 group, special Euclidean group. And we need to redefine what the plus and the minus operations if we still want to use this diffusion process. The second part is how can we define these Brownian motions in this SO3, in these groups. So there's some of the work has been done, and we borrow this framework and helping in many of the areas for us in the generative AI. And by doing this, we can better understand the first problem in the high-dimensional densities. I'm briefly can talk about the first problems. I feel like this is really important, and for statistics, and many work can be done in the first areas. The second area is the data augmentation and the labelings. If we talk about data, actually we can safely claim probably like 99.99% of the data in the real world settings is unlabeled data. How can we better leverage the majority of the data is a very challenging problems. And people talk about kind of annotations and the labelings, but annotation and the labelings kind of in the traditional naive way probably not works very well. And we know the expert have a limited time to doing the work. And we also know each annotation is not equally important. How can we use our limited time from expert to annotate the most important data, most informative for helping us? That's the the problem that we want to try to solve. And for the past few years, we have been trying to do the research in this area. Annie and myself and other students have one paper published in JASA and helping to solving the relatively low dimensional problems. But in the higher dimension, in the in natural language processing, in the medical image, we're still looking for some of the solution in these areas. So this data annotation and the labeling. So the third part is the reproducible research. And during the yesterday and today, we talk about a lot of this kind of topic on reproducible research. One of the challenge of the reproducible research is we don't know how large of this null hypothesis, the null space. And for example, if we know the linear models can have one model, have one alternative model, have two models, and the model space is relatively small, then I can know what's the kind of chance of the false positive. But on the other side, if we use some of the other methodologies like random forest, or some other method, it's a very like a deep learning, tuning the parameters. We don't know how large of this null space. The larger the null space is, the larger chance we got the false positive. How can we systematically to quantify this? That's the very challenging and important problems for many of the drug discoveries for us. As yesterday, Peter made a very good point is how can we build the infrastructures to enable us to do this? We have some preliminary approach, like for example, use the kind of version controls to know what all of the model histories, and but how can we incorporate this and to better estimate how large of the model space will be explored that can better helping us on this reproducible research. So this is a third topic. The first topic, and we are interested in how can we better use the totality of evidence. Yesterday we have some talks on the multimodalities. We briefly touched on these problems, but it's far from kind of the satisfactories. And so, for example, how can we combine this literature data? And over the lunch we have talked about is during the past many of the statistical approach and are now handling the papers as a covariate. And these days we just use a paper, download the paper, and the paper have many of the descriptions, either track the information, use these published PDF files at our covariate information to predict the drug properties. And so we are doing something like this. And beyond this, we also want to combine all the evidence, the animal studies, preclinical studies, and to better helping us on this to form this totality of evidence, the multimodalities of the predictions. So in the end, we are kind of also very interested in the trust and these data sharings. And people talk about what's the number one waste for the companies, the waste kind of the talent of the people. The reason they have a significant amount of waste is because of the trust issue. Many of the trust issues. And I didn't see kind of if we can all the trust is the cost, and if we can better the trust the kind of this each other, kind of better trust the data source and better do the data sharings. That's one of the fundamental problem fundamental problems. How can we better leverage the algorithm to solving in this area? We are exploring some like a for example, the multi-party computation. The multi-party computation is we want to share the data, but the data can only use for one purpose, just can be used for one purpose. So for example, if I'm interested in the average salaries of these 20 people in the room, so very simple algorithm, I can generate these 20 random numbers, but I'm forced the mean is equal to 0. But these numbers is really, really large. For example, the first number is 13 billions and have multiple decimal values, and added your salaries on top of these numbers. And you will be more safe to share this data. After share this data, the average will still be the true average because this we generate random numbers, we force the random number with the mean is equal to 0. But the story behind of this is there's some algorithm, and they can force the data can be used for calculation for only one purpose. We will calculate the mean is correct, but the variance is incorrect, the quantile is incorrect. So how can we better to serve this purpose when we share the data can only serve the one purpose. For example, the multi-party computation could be one of the solutions. Differential privacy is another part of the solution, but they also suffer some of the the limitations. But in general, this belongs to the directions. How can we better use the algorithms, data analytics, helping us to quickly form the trust and to serve the purpose and for the data sharing. So these are the top the 5 things that I will think about is important. So and we talk about the the positions and what's important for the individual statisticians. So I'm thinking it's important to continue to think about what's the big problem to focus on the social impact. And among all of these things, I'm thinking it's also very important to train our people as statisticians. How can we make our students or the next generation scientists, or even include ourselves, be more curious? Once we become more curious and we want to better understand the science, we want to be better to understand the bigger pictures, we want to own the problem, we want to own the problems. I continue to feel like we see our people and our new hires. Some people only define themselves as statisticians, only focus on the number of questions doing the statistical work. But on the other side, some people define themselves as a scientist and want curious to understand the bigger picture. I was thinking how to continue to nutrite, doing the nutrition of our curiosity is a very fundamental thing and for our next generation statisticians. And the next one is we need to understand the whole paradigm of the research is changing. I like reading the book, the Sapiens, A Brief History of Humankind, and they talk about the human beings have the 3 revolutions. One of the revolutions is agricultural revolutions that make us from the huntings to the farmings. The huntings means like a couple of people and the small troops can do the work. But these days, when we're doing the science, it's not hunting anymore. We are doing the farmings. Then in the broader collaborations with the bigger groups. And how can we continue to develop the mentalities, think about these collaborations and better understand what other people do. That's the really the fundamental and helping us to grow the expand our influence. So the new training structures and the reward framework is also important, I'm thinking, to accelerate this. And the trainings is, I feel like many of, we probably need to continue to encourage our students, like some of the fundamental classes are very important. For example, the operation, the numerical optimizations, operation research, some of this, the work, the optimization is truly form the foundations. Many of the, actually all the AI machine learning problems can be formed as optimization problems. And also understand the optimizations not only help this practical use, and also help our theoretical statistics. Think about like the Lasso, and in the Lasso on the Oracle property predictions, they use the form the KKT conditions and to prove this. And they also helping us on this, and also helping us on the if you think about the curvatures and this variance estimations, and many of these are got connected. So in the end, we'll probably also think about what's our reward frameworks and how can we better reward people to doing the science and make a bigger impact just beyond the publishing in the top 4 journals. So I think that's it. And so thank you so much. I think 100 years ago we had I counted this number of peoples, and exactly this we have the same number of peoples compared with yesterday. Okay.
I have two questions. So being a person who on the driver's seat, I wonder why Eli Lilly want to invest to create this division of AI in your company. What you guys are doing? And what's the role you play in the drug development? That's first question. Second question, if we have better solutions or some smart solutions, is there any channel that we can really help, contact your company and help your company to deliver or, facilitate the research in your company? How we're going to do that, to process that? Do you have any suggestion or some insights to share with us?
So I'm thinking kind of share a little bit of stories. And originally we formed a team about 6 years ago. We are the people like 5 or 6 people, the PhD. Right now the whole team, just in the US, full-time employee, the PhD. In my team already have 30 PhDs, including kind of plus myself, from multidisciplinary. So the question, the reason that this group is increased is that we continue to demonstrate the values for the company. We just continue to think about what is the most important problems for the companies to use kind of analytic AI machine learning to address the problem. Just to give a couple examples, in the last year, we finished the first de novo design to generate the large molecule, to generate the drug, and helping the companies. This make one of the breakthrough. And also, originally, we focused on the digital health in some areas, and we developed some of the app and the solutions better to quantify the Alzheimer's disease and also the Parkinson's disease. Over the lunch, we talk about this. So to make a long story short, continue to focus on the big problems, starting from the companies, and deliver the values and demonstrate the values, talking to the people, demonstrate the value. This is the reason our team can continue to grow. So this is one part. This is one piece. The second bit, you mentioned the collaboration. Actually, we do have many of the collaborations with many of the folks sitting in this room, and we continue looking for some of the collaborations. I'm thinking the collaboration from 2 ways. One part is we continue to disclose what the problems that we are most interested in. In my personal GitHub, I already post 20 or 30 of the statistical problems and what is relevant for us, and also from these informal channels. And so I'm pretty interested in the high-dimensional density estimations that can help in the digital health in many of the areas. And after the presentation, many people talk with me, and we have formed these informal collaborations. At the same time, I also more than welcome, because I don't know what I don't know. A lot of time, the people just meet with me and show, oh, this is really important research we recently did. And that's influenced a lot of my research. That influenced a lot of my research. For the past many years, I'm doing the treatment recommendation. That started from a very initial discussions with Professor Michael Kosrock at the moment. They showed me one of the papers and cite Susan's original paper. And so we started working in this area. We started working on the areas and generated some of the research. And we even launched some small trials to verify this this dynamic treatment regime in these algorithms.
Is rich. So why have they talked at all about, how Amazon has that Amazon Scholars Program where different, so have you ever talked to the guys, the upper people at Eli Lilly about maybe having a scholars program? Because that really, I think Amazon is benefiting grossly, in a positive way, by their scholars program. So what's Lilly's plans for a scholars program?
I'm so glad you mentioned this. Actually, we have we just started to form this so-called Lilly Academia Network, and so we are looking for some of the collaborations. Like if the professor taking the sabbaticals, and we are starting to form this program to welcome to come to Lilly's and start to have this, and also spend maybe 1 day. If they're not taking the sabbatical, spend 1 day working with the Lilly on the project. During the past, we have been informally doing this, working with Harvard and working with some of the professors. And right now, we want to make this even more formal, have the process of doing this.
That's great.
Yeah, thank you for mentioning this.
That's great. So maybe we we move to next talk, and next talk will be given by Maxine Padnov, is a faculty of this university, and then I think Maxine had a twinning in Russia or somewhere, and then come here as the faculty, and so okay, thanks.
Okay, while presentation is loading, I first of all want to say thank you for organizers. I mentioned among organizers, but I actually have not been one. And yeah, so I'm very happy to be here, and I'm here with a machine learning department. However, I was educated as a statistician. And however, the community I was growing in, it was completely different from this community. It was a really theoretical statistics community where people only care about minimax rates. And if you ask someone about simulations, it can be sometimes considered as an insult. So yeah, that's only partially a joke. Yeah, so. And I really enjoy being in this conference because this community is very, very new for me, but I really like the amount of attention which is paid to the actual practical result and about like the proper statistical ways to achieve them. And I think I already learned a lot, and I'm currently thinking whether I'm doing right things in terms of like my research based on all the nice ideas that we discussed here. Yeah, and one thing about my research I will be talking later that I understood that probably it is relevant because in every second talk people were mentioning uncertainty quantification, but without, I think, in any talk mentioning the solutions for that. So I will be talking about one of like partial solutions possible. And yeah, so let's go. Yeah, so the session is called Smart Health, so I need a slide of Smart Health, but as you will see, my research is not really applied, it's more, can be called applicable. And however, motivation is really relevant, so in modern like health infrastructure, we are dreaming about having all this network of interactive agents, which can be hospitals, it can be some home-based healthcare, it's mobile healthcare, and so on. And ideally, what you want to achieve, you want to have all these devices, sensors, and predictive models learning together, but without sharing the data. And for last 5 to 10 years, it was like really fastly growing area of federated learning, where the models try to learn together, but without sharing data, or with sharing data, but in a way that you keep privacy. And such systems, they have some unique properties, which are interesting from a statistical point of view, and mathematical point of view in general. One of them is statistical heterogeneity, which means that agents, they may have different distributions. Say, think of the hospital in UAE and hospital in Italy or France. The even age profile will be very different for these countries and hospitals, and it should affect our choice of the best model and of decision thresholds and so on and so forth. On the other hand, also there is a system heterogeneity there, which means that the devices are very different, they are not always available, and you should construct your learning procedures in a way that you take that into account. And the system heterogeneity was considered a lot in the community. There exist multiple, dozens of algorithms which do distributed training in various, sometimes very complicated scenarios when you have no central server, or irregular updates, and so on and so forth. However, if we start to speak about statistical heterogeneity, much less has been done. There has been certain amount of works on personalization, so when you learn collaboratively models but which are tailored to a particular distribution of particular agents or group of agents. However, I don't think that there are many very satisfactory solutions for that. And one thing which I really interested in personally is to do uncertainty quantification, which means predictive uncertainty quantification. So confidence sets, confidence intervals, and so on. And my goal will be to go for some solutions which allows personalized confidence sets for particular agents here in the system and with a confidence level which can be guaranteed. So more formally, what I have, like generally for uncertainty quantification without a federated system yet. So I have some data coming from some distribution. I probably have some predictive model which has been learned somehow. And now what I want to construct the confidence set for prediction. So I have new observation X, there is a random label Y, and I want to have my confidence guarantee. However, the modern machine learning and deep learning application limit our abilities to apply like classical statistical methods. Why? Because we want minimal assumptions on the model. We can't really use asymptotic normality in many cases because you have very many parameters and so on and so forth. And also you don't really know the distribution, say over images or over whatever space you have. And you also want minimal assumptions on the distribution. And and the result of what we want to have is something like that. So we have, you see, different images of squirrel here. And on one picture, on the first picture, we see the squirrel very, very clearly. So we have 99% probability, and our confidence set contains just one class, fox squirrel. However, on the next picture, we see it from the front, and also might be some might be a question whether it's really fox squirrel. That's why our confidence is bigger, and also there is a bucket there, right? That's why we have two classes which corresponds to a bucket, so the system is confused. And finally, we have the last picture where it's partially cropped and so on, and already we see that the first class is not the correct one, so the most probable class is marmot, not fox squirrel. So that's an example of the result we want to have, like in the simple case of image classification. Then speaking a bit about this possible solution. So one topic and one, I would say, family of methods which gained a lot of popularity in machine learning community recently is so-called conformal prediction. Here I present one particular instantiation of this approach, which is called split conformal prediction. And it's very, very simple. Actually, it's almost look naive. So what you do, you identify a heuristic notion of uncertainty, which can be, say, absolute value of a deviation or something else. And then you assume that you have certain calibration data. And what you do, you compute this score function, which measures your uncertainty. You sort the values of score function for calibration data, and then you take specially tailored quantile, specially tailored quantile of this distribution. And then your prediction set for a new input X test is a set of labels Y, which has the values of score function less than this quantile. So very, very simple procedure. However, you can prove some pretty strong guarantees for that. So for example, you can prove that the probability that your new point comes to the confidence set is greater than 1 minus alpha, what we wanted, and also it upper bounded by 1 minus alpha plus 1 over n plus 1. So it looks extremely strong. Of course, there is no free lunch, because, for example, this guarantee is not conditional on the calibration data. It's also averaged over calibration data. That's why the convergence rate is so fast. However, still looks very promising, and no any assumptions on anything except for independence. Just a small historical note that conformal prediction was developed in mid-90s by Vladimir Wolf and his collaborators. And for those of you who don't know, Vladimir Wolf is professor in Royal Holloway University of London. And probably a little bit less known fact that he was last PhD student of Kolmogorov back in the 80s. So, okay. Seems to be too good to be true. No assumptions, strong guarantees. But in fact, of course, everything is dependent on the score function. So if your score function is very bad, then your guarantees will be very vague. And on the other hand, if your score function sorts your objects in a, like in an order of increasing uncertainty, then it's gonna work well. And yeah, so now we come back to our example. So we want to apply something like conformal prediction, but to our heterogeneous system. What could we do? First of all, we still need to do some assumptions now. And my assumption will be, just for simplicity, that my agents, they differ because of the covariance shift. So I assume that, okay, better I will show by hand. So that the distributions for different agents are different, but they are different due to a different distribution of covariates, while the likelihood is the same for all the points. And what I want to do, I assume that I have some global model which predicts for that, and I want to do personalized confidence sets. I should note that here the assumptions of usual conformal predictions, they are completely violated because the data is not identically distributed anymore. It's not exchangeable, which is a general condition for conformal prediction, and I need to do something to account for that. Yeah, so the goal, and what is important, yeah, that's what I didn't mention, is that I want to do confidence set for a particular agent. So what does it mean? It means that I want my prediction set to be tailored to the distribution of a particular agent, but I want to use the information from other agents, because there might be some similar ones which contribute to my knowledge about the distribution of my agent. So I want to share information, but I want to be personalized. Yeah, very quickly about the approach, how can you do it? If you assume that somehow you have access to the importance weights, to the fractions of densities for the test distribution compared to the distribution of a calibration data, then you can proceed. And how the procedure works, based on the importance weights, you can construct special weights, which I call quantile weights, so certain renormalized importance weights. And then, instead of computing the usual quantile as for the standard conformal prediction, you compute the weighted quantile. So each point is weighted with a certain weight. And this weight determines basically the relevance of this particular point towards my test distribution. Okay? Then, what you can prove that empirical miscoverage rate, which is now conditioned on a distribution, conditioned on the calibration data, it's not far from the target miscoverage rate. So basically, and not far is something of the order 1 over square root of n. So two notes here. One is that this result is stronger than the one for the standard conformal prediction in the sense that now I have a conditional on calibration data, which is important for applications. You don't care about all possible calibration sets. You care about the particular calibration set you have. On the other hand, the price for that the rate is worthy. So it's not 1 over n, it's 1 over square root of n. Right? Then, of course, that was theory. The practice is that you need to estimate many things to apply the procedure. The previous theorem, it assumed that all these importance weights are known. But then I have my images. What is this, the density of test point over the calibration distribution? No one knows. And you need to estimate that somehow. And the second thing, we are in a federated scenario, which means that you need to estimate all these guys in a federated way without sharing the data and so on. So ideally preserving privacy. And that becomes complicated. We have some partial answers for that in our ICML paper last year. And, but still a lot of work to be done. And yeah, but some partial results, again, for almost a toy example. So what we did, we considered the ImageNet data, but not just the usual ImageNet, but also the corrupted images. So you do kind of different corruptions like blurring and so on. And there is a data set which called ImageNet C, which has 5 degrees of corruptions. And so we considered the data which are agents with a different degree of corruption. So some with original ImageNet data, some with the corrupted data. And we basically used our procedures. So we wanted to construct a confidence sets. So the first picture is about coverage. The proposed method is in blue, so we asked for 0.9 coverage. It worked pretty well. The green method is the local one, which ignores all the data except for the particular client or agent. And you see it also has correct coverage, but the variance is high because you're using only the local data. And then you may use like standard conformal prediction, which is in orange, based on all the data, and then because of the data shifts, it completely fails. The next plot is about the size of a confidence set, and here we see that, well, the situation is not so nice, because even for moderate degrees of corruptions, the sizes of confidence set are very large, like more than 10 classes, 50 classes, and for a large corruption, you see like more than 100 classes, which is not very nice, but well, that's what we have. So here I come to the end of presentation and few remarks at the end. So first of all, I think that uncertainty quantification is indeed like important for the real world applications. And with the help of statistics, you can make a valid prediction set which have guarantees. However, of course, there are still significant gaps to applications. And for example, I didn't talk about how we estimated importance weights here, but actually that was very like ad hoc procedure here. And so looking into the future, I think that it's interesting to do uncertainty quantification for personalized models, for the transfer learning and so on. And also we are working a lot on the extensions to like other domains like time series or texts and so on. Yeah, so thank you very much for your attention.
Any questions from audience? Xihong.
That was a great talk. So how can you do this work without making the assumption about distribution shift?
You mean, okay, so you mean this point, like extension to general types of shifts? Or,
yeah, exactly.
Yeah, so in fact, the story is as follows. So one possible direction you can do is that actually everything in this methodology is based on the distribution of scores. And for example, what we are doing in the method, going back, we use these importance weights, which is something very nasty, which are fractions of densities in very high dimensional space, probably. Very hard to estimate. But in fact, what you can do, you can look just on the space of scores, which is one-dimensional. And for example, if you have you use part of your calibration data to just estimate the distribution of scores, which is already one-dimensional, then you can do this, potentially. That's one possibility. And you don't need to do any assumptions. You can do it completely empirically.
Other questions? I do have a question. Can you turn to the next page? Yeah. So I suppose the alpha is the significance level, right?
Yeah.
It's a 0.05. But I'm thinking that, how about the C? Why the C is uniformly constant, that independent of alpha? Suppose I want to do this approximation for 0.05 and 0.01 or 0.001. Why they would have the same rate? Because I think it's much harder to approximate your confidence coverage rate, like for 0.001 versus 0.1, right? It's much easier to cover to construct confidence at the level of 0.1 rather than 0.001. I just wonder, like, what is the C? Does the C depend on actually the choice of alpha or not?
Yeah.
And that's my intuition. I don't know. I mean, my practical work, I feel that it's much harder to approximate a very small number versus.
Yeah, of course. Yeah, so the tails are much harder to approximate. I think you are right. So I think I'm a little bit collapsed here because I also don't write the expression for this guy, which also involves delta and so on. So I think you are right, but well, yeah. So you can do some upper bounds, and I think that's what we've done. But if you really want to do very precise bounds, it should include somehow.
Great, thanks. If there's no more question, then we move to, thank you so much. Then we move to next talk. And so this is the last talk of this session, or maybe this retreat, but not least. That's will be given by Chen Chun-Shi, and he's associate professor in the LSE, right? London School of Economics.
That's right. Many thanks for Tian and Hong to invite me here, and it is really a great honor for me to deliver a lightning talk this afternoon. And prior to the talk, Peter sent us like 4 questions. And to be honest, when I first saw those 4 questions, I'm a bit shocked. Am I supposed to answer those 4 questions? So I feel like those 4 questions, they are too big for me to answer. It should be answered by you guys. And originally, I also thought that the purpose of me visiting the university was mainly to learn from you guys and to learn from your talks, to learn from the discussions, and probably also to briefly travel around. I didn't expect that I'm being posted into such a position to answer those 4 questions. And also, many of you have already provided many answers, sort of for insights into those 4 questions. So in my talk, my purpose is just to try my best to provide some additional thoughts, in addition to those that you have been provided based on my limited experience and knowledge. And I probably will not answer like all those questions. So first I will directly jump into the 3rd question about the open research questions. So again, I think you guys have discussed like many important research questions. But I feel like one of the questions that has been less explored corresponds to the problem of fairness. So according to my experience, so when I talk to some of the health scientists, I feel like they really care about those fairness issues. So they believe like those AI, although they believe that those AI algorithms, they might be effective, they might be efficient, but they do not believe that those AI algorithms, they can make fair decision rules. So for instance, just to consider like a very simple example. So suppose we have like 2 patients. One of the patients is like a very young patient, and the other patient is like an old patient. And suppose we can only treat like one of the patient. Now suppose we know that if we apply the treatment to the younger patient, he's or she's more likely to survive. Then an AI algorithm will, for the purpose of maximizing the efficiency, it will recommend the treatment to the younger patient. But that's not like a morally fair decision. So how can we develop reinforcement learning algorithms? How can we develop policy learning algorithms to ensure the fairness? Okay. And the next point, I guess it has been also mentioned by Annie and also Hao Da and Tianxi in yesterday's work, and Maxima also discussed a lot on this. So it's about privacy. So medical data, they can come from multiple sites, and how can we pull all the data together to enhance learning while preserving the individual privacy? So I feel that's a very important question. And also that's related to like federated learning, which Maximo just talked about earlier, and it is also related to like a new recent concept on decentralized AI. The 3rd question, I think this is like a long-standing problem in medical health, and Susan also talked about this in the morning during the keynote speech. So I basically refer to this problem as like a double inhomogeneity problem. Now, if you consider like those mobile health applications, So the data structure is quite similar to the panel data structure. So on one hand, you have like multiple patients. Now, on the other hand, for each of the patients, you have like a longitudinal type data. It is like a time series data. So that data structure is very similar to like a panel data structure. And among different patients, we do have like those patients' heterogeneity, and over time, we also have like such kind of non-stationarity. So for instance, typically in medical studies, the treatments, they are decay, they will decrease over time. So that's one sort of non-stationarity. And the real world, it is always like a non-stationary system. So there are many other sources of non-stationarities. Okay, so next, some other open questions. So in order to obtain like a high quality AI system, so data is like the key to build and to train those AI systems. So how can we collect the data? And in statistics, there are some like research topics that are related to the data collection process, which it's like experimental designs, and this also been discussed by Professor Kang Jian and also some others earlier. And also the second bullet point, active learning. This has also been discussed by Hao Da. So how can we adaptively choose which of the labels that we should annotate, given the limited budget and time of those experts? And the second point is on data integration. So how can we develop transport learning and semi-supervised learning techniques to combine the data together to enhance learning? And also, how can we like incorporate the power of large language models to improve the learning? And that might also be related to the last point on knowledge distillation, which is also briefly mentioned by Hao Da. Okay, so the second question, how should an individual statistician get to contribute? Again, you guys have discussed, has proposed several suggestions, and I just want to add some additional thoughts based on your discussions. So firstly, I think it will be important to continue to learn those state-of-the-art techniques, and combining those techniques with your expertise may yield new algorithms, may yield new methods. And take my experience as an example. So in the past 4 to 5 years, I have been learning reinforcement learning from Susan and also from those computer scientists. And I have to admit that I learned a lot from them. And now, when I view reinforcement learning, I will not only view it as like a powerful machine learning algorithm for the purpose of policy learning, but I will also view reinforcement learning as a tool to solve like many other problems, to solve many other questions. And here are some of the examples. So in the firstly, in the past 3 to 4 years, I have been working on like ride-sharing company. And 5 years ago, I take an internship in the ride-sharing company. And I became interested in the A/B testing problem in the company. So how can we assess the effect of a newly developed policy compared to an old policy? And when I asked the company how do they do A/B testing, they told me that they use like a standard two-sample t-test. But standard two-sample t-test has its limitations. So if you consider the ride-sharing application, it is like a very complicated dynamic system. So if you use a two-sample t-test, it will produce like biased estimates. So basically, the ride-sharing is like a dynamic, highly complicated dynamic system. So the past treatments, they will also impact future outcomes. So if you use a two-sample t-test, it ignores those carryover effects. And what we have found out is that the reinforcement learning framework, it is a very proper framework to capture, to model those carryover effects. So that's one of the examples. And another example is related to what we refer to as a dynamic mediation analysis. So what if you have like a mediator that evolves over time? And that's also mentioned by Susan in the talk in the morning. So how can we assess the dynamic mediation effect? So what if the mediator not only affects the current outcome, but it will also impact like future outcomes? And again, we found that like the reinforcement learning provides a very natural framework to model those effects over time, to model those dynamic systems over time. And lastly, causal inference. So there's a line of literature on causal reinforcement learning in the machine learning. And next, some ongoing works. So again, I feel first bullet point. So we recently found that reinforcement learning, and in particular offline reinforcement learning, it is also a very nice tool that can be applied to solve the transfer learning problem. So we can borrow some existing like offline reinforcement learning algorithms to enhance the performance of transfer learning. So that's what my current ongoing work. And we have designed some simulation studies and found the proposed method works well compared to baseline algorithms. And finally, also IL is a very nice tool for constructing experimental design to solve the classical experimental design problems. So that point has also been mentioned by Professor Kang Jian in yesterday's workshop. And next, sorry. And another point I feel, I think during yesterday's discussion, so we have reached like a consensus that currently the statistics literature folks, the statistics community focuses too much on the math and focus too much on the series. And now I have been graduated. 5 years ago, I graduated from my PhD university from NC State. So if I look back to what I have done 5 years ago, I feel that I spent too much time, I wasted too much time in writing the proofs, in writing the series. In writing papers like with over 100 pages, so like 30 pages for the main text and like another 90 pages for the supplementary article, which probably no one would read those supplementary articles. So I just feel that I spent too much time on writing the proofs. If I think about what I have done 5 years ago. Now, in the past 3 to 4 years, I have been reading like those papers from the machine learning literature, from the reinforcement learning literature, and I feel in machine learning there's also like a group of theoretical computer scientists. There's also a group of theoretical machine learning researchers that write series papers. And I found that they are very clever in writing the series. They are very clever in writing the series. So they focus on writing the simple series. So series under the simplest settings to demonstrate the main idea. So that's probably one of the practice that we can do. So just to give you an example, for instance, they welcome like those reinforcement, what I refer to as reinforcement learning alone series or deep learning alone series. But they will not consider like their combination. They will not consider like combining those DL and IL theory. So if you can demonstrate the performance of the algorithm, of the IL algorithm under a very simple scenario, why would you consider to incorporating it with deep learning? So I think that's one of the example. And also they will focus on very simple settings. They will focus on very simple settings to prove the series. So for instance, in reinforcement learning, typically people will focus on tabular settings. So everything is discrete. You have like discrete states, you have discrete actions, you have discrete reward. Of course, this is a very restrictive setting, but it is mainly used to simplify the analysis. And secondly, they will usually impose like those independent data assumption. If we think about it as a statistician, so data, they are generated from a longitudinal study. So how come the data can be independent? And those computer scientists, they also know that this is a very strong assumption. But they are still willing to impose this assumption, not because they do not know how to extend those assumptions, but because they feel like it is unnecessary to use like those mixing type conditions. And finally, like they also typically use like a finite hypothesis class assumption, so which basically means that the parameters that the value of the parameters that it can only take like finitely many values. And again, they know like this kind of assumption, they can be generalized to more like general VC type conditions, but still they are willing to impose those assumptions to simplify the theoretical analysis. So I feel like based on my experience, so if I think about this practice, I feel that these computer scientists, they are very smart in writing like those simple series to save the time to demonstrate the main idea behind this series. And finally, I think this point has also been mentioned a lot during yesterday's discussion. Now, if you think about the machine learning community, I think one of the reasons that it can achieve such a large impact is that they stick to those benchmarking data sets. So as Annie mentioned, they have like many publicly available data sets, and Annie mentioned like the UCI machine learning repository, and Susan also mentioned the OpenAI Gym environment, which is typically used in reinforcement learning. And by the way, I also want to add that it is an open environment, so you can also add your new environment to those modules. And in the past 3 to 4 years, I have been working on the application of ride sharing jointly with Hongtu. And now we do have like some benchmark environment so that we can evaluate different type of reinforcement learning algorithms. So specifically, we have like designed a very simple environment to simulate the ride sharing dynamics. So 2 or 3 years ago, I taught like a reinforcement learning course at LSE, and at that time, I asked one of the PhD students to wrap up the code for designing those ride-sharing environment, and of course, like we use the money from the department to pay the student as a TA, but later we managed to upload the code to GitHub, so it can be used publicly. And we also use real data sets to construct simulators, real data sets to construct more complicated simulators to simulate the entire dynamics. And also, we have students sent to the companies as interns to get the real data sets to evaluate the different performance of the algorithms. So that's all for my talk. Many thanks for listening.
Talk, and now question. Oh, okay. I mean, he's a local person. We should give him opportunity. I'll come back to you guys.
Yeah, thank you very much for a very interesting talk. I just wanted to make a point on your theory and how much we should simplify it and so on. Just I'm very much immersed in machine learning community personally. I much more work on machine learning than on statistics, and I could say that quite surely that within the machine learning community currently people are really tired of the theory which often is done just for the purpose of having a theorem. So people are oversimplifying the things to the extent that the theorem doesn't give any insight on anything. And I don't know, 4 out of 5 theorems which you can find in machine learning conferences will be like that. So that's why I personally suggest to be very, very cautious, because of course, if you have a simple model which gives you a lot of insight, that's very nice. But unfortunately, the current practice is that people study the simple model which doesn't give any insight. So that's a big problem actually in the community.
Yeah, thank you for the comment. And I'm referring to those series that mainly used to demonstrate their main ideas, but under those simple settings. So if they can demonstrate their ideas already under the simple settings.
Yeah, I think I want to echo the point on this. I personally, I respect people doing theory, okay? And at least in the last 5 or 6 years, my personal view is about why I'm concerned about the people working on the theory is, you think about deep learning as an example. And if you look at all the papers approved so far, published so far, my understanding, they basically try to approach these very difficult problems from harmonics, analysis, this kind of method, functional analysis, right? But do you think that are the right mathematical tools to solve the problem? I personally don't agree. The reason that's also comments by other speakers, because do you think that's all these functional space we considered, and we put all these bond? Practically, it's usually for us to construct better architectures to improve the performance of deep learning in practice. Any of this theory works that way. That's my personal understanding. The problems. I talked with Vijay on this. Could you classify, could you prove a theory, really basically say this, because of these mathematical results, help me design better architecture for that purpose? In what sense? Nobody. That's the basic, I'm not questioning this. That's the reality we are facing these days. Maybe Susan has a different opinion, but that's my general comments on this.
Okay, so do you have any response to? He just finished. Hongtu just finish his comment. Do you have any response to this comment? I mean, just go one by one. No? Okay, like Hao-Da, go next. Oh, Hao-Da will answer a question. I will give them response. Okay, that's fine.
Actually, we also need some theory, some areas. So I was involved in the CataGo development. CataGo is an open source version of AlphaGo. They are heavily used on the deep reinforcement learnings and the Monte Carlo tree search. Right now, we include it as the Monte Carlo graph search. But there's a key formula, the POCT formula. The POCT formula is the balance, the exploration, and the exploitation. But right now, there's no good theory to get this. Many of our development is just to try different form of these formulas and tweak the parameters to improve the learning rate. So if there's someone to develop better methodology, better theory on this, that can significantly guide on the Monte Carlo tree search algorithms. But actually, I have one comment and also one question for the talk. So you mentioned this double heterogeneity. But actually, there's a triple one. The third one is the patient preference. I want to share the story for here, the patient preference, because some patients, even for the same efficacy safety, some patients more prefer efficacy and another patient more prefer safety. Because the patient preference is different, they get another layers of the personalized medicine. But actually, this kind of very interesting thing is many years ago, when I was present the kind of ITR framework to our physicians, kind of dynamic treatment relief personalized solution. Our physician asked the question, why you assume the physicians didn't make an optimal treatment decision? Because all these reinforcement learning is assumed other physicians didn't make an optimal treatment decisions, but optimize one of the target. Physician asked me, why you assume we didn't make the right decision? Maybe you are wrong. Our physician makes the optimal decision, but we optimize for the different things. So the question that come out is, how can we, from the real world data, we can better learn the patient, if we assume the physician make an approximate optimal decision, we can approximately learn the utilities of the patient preference or the physician preference for different type of the patient. That come out with some research or the reverse the reinforcement learning. And that added additional layers of this patient preference heterogeneities. They call it kind of triple the heterogeneity. My comment for here is, when we deeply interact with the physician, a lot of times physicians really ask very good questions that motivate our research. But my question for here is, at the first part you mentioned the fairness. So I'm just curious, the fairness for the reinforcement learning is a real question or is not a real question? My point for here is, because all the reinforcement learning, we try to optimize the total reward. To optimize the total reward is if and only if we optimize it for each of the individual person. If our model space is flexible enough, so our model space is the flexibility is increased with the sample size, and eventually we are going to optimize for each of the individual. I didn't see any of the fairness problem for here for the individual person. So what do you think about this?
Attention, can the speaker respond? Then you respond. Can you respond first? I know that this is a very hot topic, but can you respond?
Yeah.
Is there any fairness question in the reinforcement learning when the patient space is large?
Thank you for Peter for summarizing the question. So firstly, I just want to respond to the comment that Hao-Da made. So for the physician's question, I think not all the data they are collected from those observational studies. And we also have randomized data collected from randomized trials. So in those data sets, like the treatments, they are randomly assigned. And the physicians, they are not, they are not assigning the treatments in those data sets. So that's why individualized treatment decision, they can help. And also, even if the physicians, they make the optimal decisions, so you can also develop statistical learning methods to possibly to improve their performance. And also you have also mentioned like the inverse reinforcement learning. So that's another very good point on incorporating physicians' recommendations into this problem. So that's my response to your first comment. Now for the second question, I think. So at least based on my experience, when I talk to some of the health scientists, they do care about the fairness issues in reinforcement learning. So you suppose like if you give like different decisions to different individuals, then people might worry like if the decisions that you make, they are biased toward certain race, towards certain gender. And I think that's a concern, at least based on my knowledge from my interactions with a health scientist. Does that?
Anyone?
But if your response is very relevant, I think
Yeah, I think it's just fundamentally not right if your decision involves, for example, an interaction with race, for example, and they have very little data, so you are basically artificially downweighting them, right? Their contribution. Let's say you have 1%. So it most doesn't matter what their loss is. You're not going to amplify their effect. So I don't think that particular issue can be mitigated, assuming the true model is correct. The true model has an interaction, basically, let's say, between race and all the effect, right? So it's...
Annie, sir.
Oh, okay. So I'm continuing about the theory. I just want to say we don't make a very kind of absolute, nothing is absolutely wrong or right. So I think Chun Chun made a good point, because I think that point is that when we develop theory, sort of people know the general idea that theory works. We don't need to take care of every details, every combination. We say it works. What's intuition behind it? So that makes sense. So you don't want people read 100 pages, understand the idea behind it. But also, I think what Hongtu is a little bit too extreme. I think I appreciate the theory because we. No, it's okay. You can talk afterwards. I just feel like I'm also developed theory. Let's say red metric complexity, VC dimension, the error rate, convergence. It's important. Although in the reality, I have to admit, we all the rate to say when the number of subjects goes to infinity, when my error bound will happen, or number of observation, number of time points, right? This is very theoretical. Reality, I have a limited sample points. I have a limited number of subjects, right? This theory sort of, for us to say, okay, if we increase certain things, we get a smaller error bound. Arrow. So in that sense, I think it's useful, even though reality we might not achieve it. So I appreciate all the people did a hard theory. I think we should see both ways. We shouldn't say this is absolutely wrong or right. It's really we have to, a lot of things can coexist. Our mind shouldn't be extremist, say we don't do theory. We don't need a theory, we just do application. Or the other one say, we just do theory, we don't need application. I think we need a balance. Yeah.
Short response.
I think she misinterpreted my comments. My comments is I really like think if you have a method, if you develop some math to help understanding why this method works. Okay. The problems I'm talking about deep learning is because all the other theory they developed doesn't help us at all. Be honest with you. Everything they started with is wrong. Why do I care about the theory based on the traditional harmonics analysis? Because your starting point is wrong. That's my concern. I'm highly respect the people. I also do some empirical inference, all these things, empirical process. I'm not saying this theory is important. If we understand the problem well and basically develop the method, help us to better design and also have a better understanding why all the method we develop works in certain sense. Even in a simple example, okay, you prove the theory, tell you why I need to tune this a little bit and make this better, okay? That kind of theory is important. I'm the only question, I publish another 100 papers, and also suggestion, doesn't solve any of these simple examples on deep learning. Why do we need these 100 papers? In what sense? That's my comments, okay? You don't need to misinterpret my comment.
We got it, okay. Susan.
Okay, so I just want to walk into that little mud pie.
Who wants to join the debate? Okay.
Yeah, Xiping has to join. I was thinking of some paper I saw by Ben Yu, and it was a very applied paper. Okay, it was a very complex problem she was working on. It's really applied and quite complex. But then what she did was she had a small proof in a very simplified setting, which illustrated the main idea why the algorithm she was developing should be good. And then she used it in that real life problem. And I think in that setting, the use of simple theory, like you were talking about, the use of a simple theory, it makes a lot of sense when it's instance-based research. That is, you have this applied problem, and the whole paper's about the applied problem. And you're just supplying the theory to provide insight. Of course, I like what Annie was talking about too. I mean, it's great to have these more theoretical where they deal with all the edge cases and they illustrate that indeed there's something substantive in with a broader stroke. I'm all for that. But there's just two uses of theory here. And to keep them straight in my head, I think it's useful. Yeah.
Okay, so yesterday we talked about communications with people outside of a community. And we see examples today how difficult it is to communicate among ourselves. So I was misunderstood by others. So a lot of people believe I'm quite extreme because they don't think I like math, they don't think I'm good at math, but actually I really appreciate the theory. That's why I worked with Hong Tu and other students because they have better math. So I think we talk about we don't like methods for methods, or we don't like theory for theory. I think when you develop theory, you should solve some problems so that we can understand the method better and potentially improve the method. Mm-hmm. And some of the good examples in simple case, when we do the one-dimensional smoothing, you can see the evolution from simple method to more complicated method, including Chen-Qing's local regression. I think you can see sometimes, not always, okay? I think Hong Tu is right. Many theories, they just did theory for theory, but unfortunately, in order to understand complicated methods like deep learning, a lot of people has wasted their time to actually lay a foundation, and someday somebody may be able to really solve the problem. But I think just one shot solve the whole complicated problem is probably too ambitious. So I'm not too against the theory, but I agree a lot of theory is really waste of time, but sometimes it's necessary as part of a scientific process.
Yeah, I just want to add, because something occurred to me during the presentation, is that it reminded me of Herman Chernoff, that we collaborated for a long time, and then sometime we were working on very applied genetics problems, and he ran simulations. He wrote our program in his 90s, and then but often he would like to prove things himself. Now that he is obsessed with theoretical result, is a one way to generate intuition and understanding from different perspective. And I think in both, like, we often talk about how many ways you can prove the central limit theorem. Like, we often joke about there's an undergraduate level, there's a master level, there is a PhD level, like different. But that's just a very superficial way of thinking why we prove theorem, because sometimes it gets lost on the students. The reason why these multi-version of the proofs of the same results help is that it reflect different intuition of this very important result. And the same thing with toy examples. And toy examples are important. A good toy example help intuition, help our understand why the method works, how it works. If it doesn't even work in a toy example, if you cannot even come up with a simple example to demonstrate the use of a method, you may not have thought hard enough about that. So, but when we only focus on toy example, then that message also get lost on the younger generation because they feel, oh, it's enough to have a toy example. So I think by the end of the day, I think Heping made a comment like in a private chat about it's not something we need to change the discipline. The discipline had a very nice principled way of studying the word. It's only need to constantly reminding ourselves how we started the discipline, how the discipline was motivated by the real need to study uncertainty, to connect data, to use a combination of mathematical model and probability model to describe the random phenomenon of the word.
Great. This is a very nice discussion, debate, and yeah, it's good to make a good communication and to understand each other. And we do have 2 questions online. I think we should respect their participation and then maybe start for a second question that's related to Chun's talk. And then the first question is related to Susan's talk. So do you want to respond to the first question? The second one. Susan, you respond to the second one.
That's a very good question. I think there's a lot of advanced statistical.
Can you read the question first?
Yeah, sure. The question is that the student didn't take a stat degree, and can we recommend a roadmap of advanced statistical concepts that are crucial for these AI projects? So I think there are many advanced topics that you might want to consider. So for instance, like those deep learning techniques, those reinforcement learning techniques, and nowadays like those large language models. And I also would suggest that the best way to learn those concepts is to really to do a project related to these techniques to enhance your understanding of these concepts and techniques.
So I think the best person to answer that first question is Chenxi.
Oh, it's for attention. Oh, sorry. It's 11:30, 29.
Oh, so yeah, the question was because there's a lot of heterogeneity on how hospitals collect and store data, like, and if you want to leverage multiple hospitals, how can we put together like statistical analysis and inference to clean and work with the data? First, I would say I'm not sure how they store the data necessarily change our practice, but definitely how they organize the data and how, for example, like the coding systems differ will put in a lot of challenge. I think we just really have to be aware of the heterogeneity across, like particularly, for example, earlier I think someone mentioned like how the drugs are given within each of the hospital. They are very different. They actually have different protocols within the hospital system. Like when a particular patient come in, they have a rule to say that's a first, like how they should start, be treated, etc. So when you do that, like doing, for example, reinforcement learning, it's actually really interesting that certain paths will never be observed in the system. They don't treat this way. So you cannot even infer the what if. So that is a scenario that you really need multiple hospitals to co-train the RL model. But I think that heterogeneity definitely give us sort of like in the statistical field, a lot of, I think that's something we can work together to think about both the robustness and also, you know, what's uncertainty that we need to put forth. And I really like Susan's point earlier about the uncertainty. I'm just wondering, in the RL world, like, did people really look into I don't necessarily care what's optimal. If there's uncertainty, what about the second optimal? What if the second optimal is a lot easier or a lot, like patient preference? Exactly.
A principled way is to use a POM-DP, right? Something akin to a POM-DP. It's like you're predicting a latent state, like the latent state of stress, or the latent state of overburdenedness, or whatever. So that would be the principled way, and that is impossible to use. Those algorithms are not implementable in real time. They're just not possible. So I think you could do this in a batch. You could have a batch procedure where you might do this, but online, they just don't make sense. So everything is about a poor man's version of the POM-DP. So if we think of a POM-DP where the posterior distribution for the latent state is normal, let's just pretend, I'm just pretending, then the posterior distribution has two parameters, the mean and the variance, right? If it's a normal posterior. So what's the poor man's approach? The poor man's approach is to do standard RL adding another feature. One feature is the posterior mean, i.e. the prediction, and the second feature is the posterior variance, i.e. the confidence. And so I personally think, and we know people use the normal distribution in variational approximations, they use it. I personally think that that's going to be the one that someone's going to get it straight, and it's going to be really nice. But that's where we're going, is I want the first 2 moments. And maybe you could demonstrate to me that I need the first 3 because maybe the predictions are highly skewed. I mean, it could happen, right? Particularly in these more complex, you're in you have a lot more data, so you might want the 3rd moment. But in my world, the data's so sparse and so noisy. If I can get the first 2 moments, I'm probably good. Of the posterior, am I making sense? Do I make sense? Yeah.
Jen, I saw you had a question, but I cut it off. Do you want to take an opportunity to ask a question? Were you too sleepy to ask any questions? Okay, sure. Now I want to exercise the power of the chair. I want to close this session. I like to take an opportunity to thank all the speakers, all the people who participated in the discussion. So we will take a 15 minutes break, then we come back to the group discussion. And